This episode is the culmination of our development of the theoretical basis for representing measurement in imaging systems as a discrete linear transformation, G equals HF plus noise. Last time we emphasized shift invariant linear transformations. Today we consider shift variant systems. Here we show a particular implementation of a shift variant transformation, intended in this case for image data compression rather than image capture. We have a set of inputs coming in from the left here that are drawn from pixels in the image, and then they go into a random H matrix that puts out a smaller number, M, of outputs. Visual information is all around us. A vanishingly small amount of this information is captured. The energy required to capture, process, and store this data is the primary barrier to seeing more. Cameras commonly require more than 1 nanojoule per captured pixel. Sounds small, but we'd like to make cameras that capture terapixels or exapixels. Here we have a blind compressive encoder that is used to bring the data cost down below 1 picojoule per bit. For present purposes, however, the idea is that this device uses a matrix H to encode the data. What should H be? Computational imaging. Episode 7, Spectral Analysis. Here we revisit a slide from episode 6 with a slightly different emphasis. We are familiar with the linear transformation between objects and measurements mediated by the impulse response, G equals F integrated against H sub M. We are also okay with F of X is equal to F sub N multiplied by phi sub N summed over N, where phi sub N now is our representation basis. We can use these two equations to turn the integral equation into a discrete linear transformation. We make the coefficients of the transformation HMN is the inner product of the representation basis and the sampling functions. This allows us to take the integral form and turn it into a sum over the coefficients, which we describe as a matrix vector product. G, the measurements, is equal to H times the representation vector for F. Let's look at an example. Here we've expanded F on the Shannon basis, and we sample with the rect sampling function, and we're sampling at exactly Nyquist if this delta P, the sampling pitch, is equal to delta F. If delta P is greater than delta F, that would be undersampling, and if delta P is less than delta F, that's oversampling. Here's some examples where we've evaluated this integral numerically. So the green curve is sampling at half Nyquist. Delta P is equal to 2 delta F, and you see that the oscillations of the sync representation function are mostly washed out, and we only have about 5 non-zero coefficients in HMN. The middle curve is sampling at Nyquist, where you start to see some of the sync, and then of course the upper curve is the oversampled system where the sync oscillation is apparent. These curves are offset from 0 just to allow you to see them, and of course these are discrete values at each point where we've drawn the curve in between just to show for visualization. Okay, so now we can use this by shifting by the pixel pitch in each row to build a matrix H, that's our H matrix, and then we want to know how can we evaluate the quality of H. So for a discrete matrix, the standard method is to use singular value decomposition. Any M by N matrix H can be represented as the product of unitary matrices U and V with the diagonal matrix lambda between them. So U is an M by N unitary matrix that we think of as the basis of the measurement space. V is a N by N unitary matrix whose rows form the basis for the object space, and lambda is a diagonal matrix with each diagonal coefficient corresponding to a singular value, which are ordered according to the greatest singular value to the least. In the case of a shift invariant system, H is going to look like this. So we just take this same measurement and we shift it in each row, or the same projection, and we shift it in each row corresponding to the shifting of the position of the measurement position. So we would take this Toeplitz matrix in the form of this shifting and find the singular vectors. And we can do that for the examples that were shown for the different sampling pitches, and we get the result shown here. Now, theoretically, we would expect the singular value spectrum to be the same as the modulation transfer function for a shift invariant matrix. And we see that for this sampling at Nyquist. At the Nyquist limit here, the value of the singular vectors is 0.63 of what it is at the lambda 0 term, which corresponds to the roll-off you see of a sinc from the DC term to the Nyquist limit. It's somewhat distorted for oversampling and undersampling. In the case of the undersampled system, the singular values go to 0 halfway across the band. Here we've assumed H is a 512 by 512 matrix, but the oversampled system only has approximately 256 non-zero singular values. What this means is that we really only get effectively 256 equivalent measurements, because each measurement will of course be multiplied by its singular values, we'll talk about in just a second. We also find that the shape of the transfer function is distorted by aliasing, where you might expect, if it was a fully sampled system, even if it was sampled at the right period, even without sampling pitch, it would have a sort of sinc transfer function. When we undersample the data by sampling only at the sampling pitch equal to the width of the sampling function, we get artifacts that distort the overall reconstruction. Now, the meaning of the singular values is apparent here. If we take G and we multiply by U minus 1, then basically we're getting F represented on the basis of V. So V is a unitary matrix, again, with these rows. We can treat the rows of V as a basis for the object distribution. And we can think of the measurements we're making, that each measurement is a measurement G sub n corresponding to the magnitude of F on the corresponding object space basis function. But it's multiplied by lambda n. So we get a much stronger measurement for the first coefficient than we do for subsequent coefficients if we have this roll-off in the singular values. That wouldn't necessarily be a problem. We could just divide by lambda n to recover F. But we have this additional term of the inner product of the measurement space basis with the noise function. And that is going to create a problem. And basically the signal to noise ratio we get in reconstruction is going to be proportional to the magnitude of the singular value for that coefficient divided by the noise. So lambda n is getting smaller as the index increases, but the noise is not likely to be getting smaller. The noise may be uncorrelated to the underlying structure of the signal. So what this means is that if we look back to where we had lambda n falling to 0 for the undersampled system, those higher order coefficients are unmeasurable, and the amount of information we get from the system is reduced. This is the point of the modulation transfer function for shift invariant systems, and the singular value spectrum for shift variant systems is that as the coefficient the singular value or the modulation transfer function rolls off, we have more and more difficulty measuring the corresponding terms in the object space. So singular value analysis is useful both in terms of evaluating the strength of the coefficients that we can measure, or the strength of the terms that we measure in representing the object, and in the structure of the features that we measure. So these are the singular vectors V. So again, we're representing F on these singular vectors when we do this inversion. And the top plot here shows the first 256 singular vectors for this sampling at Nyquist, where you see now the singular vectors go from DC to higher and higher frequency as we increase lambda, and this corresponds to the idea that the singular vectors are the same as the harmonic functions for a shift invariant function. Now that should also be true for the undersampled system, but there's aliasing that comes into play because our limit for the Nyquist limit for the undersampled system is different than the Nyquist limit for F. And so we see that the singular vectors are no longer simple harmonics. They have a complex structure due to the aliasing of the higher frequency information into lower frequencies, which causes both a distortion in the shape of the singular vector value spectrum and in the shape of the singular values, and introduces artifacts in the reconstructed image. Now, so this has been a kind of a careful representation of, okay, we're going to represent F on some basis, and we're going to go and find these H matrix. That approach is actually relatively uncommon in computational imaging systems. More commonly, people use the measurement system to define the basis function for F. So in this case, for example, we say f sub n is just equal to the projection of f against the rect. This is what you might call a raw image in photography, that you just treat the image as the integral over each pixel. This is not the best way to do the representation, but it's common just because if we increase the number of coefficients f on some basis, that makes our computational problem more challenging, and so when we get into megapixel and gigapixel style systems, that approach is rarely adopted. It's still possible to try to recover the underlying f even from this basis, but we'll leave that for discussion in chapters 7 and 8. For present purposes, we want to say that, so if I could measure this projection, we measure the raw pixels, that's basically like measuring the underlying image. You might think that that's good enough, that you would just go home and say, I've measured the image and I'm going to treat the projection onto the measurements as the actual image. But there are many reasons why you might want to code the system by choose a different H to code the measurements in ways that would be more complex than an identity transformation. One reason would be because the object is actually multidimensional, and it's not possible to measure the object directly in a multidimensional system. So in this case, the common problem in computational imaging, we have a two-dimensional detector array and a three-dimensional object. We can't map the three-dimensional object onto the two-dimensional detector array, so we use some kind of coding structure to make a set of measurements that we would invert to estimate the three-dimensional object. And here we have these coded apertures. This is a figure from chapter 4 of the text, where we'll talk in some detail about what those coded apertures should be, and we'll use this kind of singular value analysis and H-matrix structure to evaluate the quality of the coding. The image shown at lower right is another reason why you might want to use coding, and this is for compression. So in this case, you have an image, it's imaged onto a deformable mirror device or a spatial light modulator, and then onto a single pixel. The reason for doing this is that you're trying to reduce the number of measurements needed to represent the image. Now, this particular example of a single pixel camera is a really, really bad idea. I beg you, beg you, beg you, please do not build one of these systems. The problem here is that physical systems exist in modes, like we've talked about at the beginning of this chapter, and it's not possible to take an image, which could be a million modes, and map it efficiently onto a single pixel. It wants to map onto a number of pixels that's equal to the number of modes in the system. Separately from the problem that the physics doesn't like this kind of solution, it's also just a bad idea to encode the image with each pixel modulated and measured in each measurement, because that's going to be a very ill conditioned system, which is what we see in this next slide. Here we have a pseudo-random unipolar H, and we're taking each pixel, and in this case a 128 scale image, and each pixel is modulated by a unipolar number and then added together with random weights in each measurement. The singular value spectrum in this case is shown at the top. The blue line is the actual singular value spectrum. In this case, the lambda 1 term, the basic singular vector, is 10 times greater than the lambda 2, so that most of the energy is going into this measurement of the average. You see the structure of this first singular vector is basically a constant across the top of the singular vectors shown at the lower plot, and then the higher order singular vectors have this kind of random structure. The yellow plot at the top is the singular value spectrum with the first order term dropped out. You see it kind of falls off gradually after the first order term. So this is interesting, and from a compressive measurement theory point of view, making these kind of pseudo-random projections can be very useful in estimating the image with fewer measurements than one per pixel. So that could be a good idea, but later in chapter 8 we'll look at the actual feature structure of images, and the features are not distributed over the full extent of the image, so it makes more sense to do this kind of coding locally within an image, where you won't have this problem of such a very ill-posed structure. So here's an example of where we're going to break the image into 8 by 8 blocks, and in this case we'd have a random transformation of each block in the image. So we take the image, and this is a common strategy in compression, measure each little block in the image, do projections on those separately, and then in this case, an 8 by 8 block, we'd have 64 pixels. We might keep, let's say, 8 or 12 of those projections, and so we've got automatic compression by a factor of 8 or so in the image that will allow us to be more efficient in our measurement system. And we'll use this in Chapter 8 to think about feature-specific measurement strategies. For present purposes, though, the idea in today's discussion is just to introduce singular value decomposition as a method for analysis of forward models in computational imaging systems, with the idea that we are ultimately going to be able to design H to have properties that are both physically attractive and mathematically attractive. So in the case of like a single pixel camera, maybe you've gone too far in trying to get the best mathematical projection you can get without thinking about does it work with the underlying physics. In the case of just directly measuring things, you haven't thought about mathematically what's the best idea. So computational imaging consists of balancing what's mathematically attractive and physically plausible. Here's an example where we've assumed that we have an 8x8 block, which means that we have 64 features in object space, and we've made 16 measurements. So we have H is a 16 by 64 matrix. We assume that we have bipolar random weights, and then we can look at the singular vectors, which are shown here as the image patches. And so these would be what we would project the object space onto. And the hope is that these correspond to, or they overlap with features in the object space that would allow us to reconstruct the true underlying object from these patches. And now we would do that jointly over the image, in which case the fact that we have high correlations between different patches in the image would assist us in reconstruction of the underlying image features. All of which brings us back to the image that we started today's discussion with. This waveguide takes in inputs from images that are already measured electronically and then can apply complex valued weights to them, since we're using a laser to illuminate the waveguide. We go through a random encoding structure and get M outputs less than the N inputs. And again, actually we have some loss here because of the reduction in the mode density of the system, but because the scale of the transformation is modest and because the coding features are not using the actual power from the original image, we're willing to tolerate that loss. Okay, so now we've got this compression, and we need to figure out how we're going to use this compressed data to recover the image. We would evaluate our H matrix based on, first of all, we'd like to make it unitary so that we have orthogonal rows in H if possible, so that we would have a flat singular value spectrum, and then we'd like the singular vectors to have a general structure that is consistent with measuring the object features that we've got. Now, this is the heart of computational imaging. We don't have pixels, we have coded data. We need to turn that into images again. That, of course, is going to be the focus of our discussion in Chapter 3, where we'll find that neural methods are the current strategy that is most powerful in doing that. That's what's illustrated at the bottom here. We take the coded data, return it into the recovered image by recognizing the features. To do that, we need to understand these neural methods, which we begin to do in our next discussion.